Hello, and welcome to tutorial number 30 of our series, where we're going to look into smoking. I don't know how to say it. Wait.
Smocking.
Smocking. Let's go with smocking, where we're going to look into smocking patterns that we can make. So the way smocking works is basically you have a piece of fabric and you stitch some parts of it together to create this kind of a pattern. And actually, let me Google that for you. Smocking patterns. There we go. Images. Yeah, stuff like this, right? And I'm not just going to show you, just this pattern, because it's not necessarily this pattern, but just this kind of a planar pattern. But rather, I'm going to try and do something a little bit more three-dimensional. So we'll try and create a column out of it. And the person who's kind of doing research, at least in the field of architecture, is Annie. There we go. This girl right here. She's working as I believe still a PhD candidate in LTH in Stockholm, and yeah, she's doing some really interesting stuff, really great stuff. So if you're interested to learn more about the subject, just Google her. There we go. Google her, find her papers, and you can read all about it. But basically, we'll just try to do something really, really simple and really, really fast. So enough of that. Where do we begin? Well, let's first find a smocking pattern. Let's find a smocking pattern that we can use. I'm thinking of... I think this is from Annie as well. So she's using fabric as a formwork for concrete, and I think that's a brilliant idea. A smoked fabric to create these beautiful patterns on a concrete shell. Let's go with the middle one, right? So looking at this pattern right here, I can see these kind of blue arrows going down on top of this grid. Actually, can we make this larger, right? So think of it as you have a mesh, right? You have all of these polygons here, and then you have these line segments that will contract, and thus the pattern will appear, right? So all of these blue lines are the lines which contract to kind of bulge out the fabric. Let's go to Rhino and let's start creating it. So first things first, I want to do a single rectangle here, and I'll do that in Rhino. So rectangle that starts at 0, and let's go for 10 by 10. That's going to be our cell size. And coming back here to look at the pattern, how does this work? Okay, so you have this segment here, and then it kind of switches and then keeps repeating. Okay, so it's going to be 4 by 2. So this whole segment right here keeps being repeated throughout the whole field, the whole surface. Okay, so it was 2 by 4. I could use array, but for this I'll just copy. Why not? Copy. Let's do it like this. Copy. Great. So we have 8 rectangles, and I'll just call this pattern base. Yeah, sure. Something like that, and I'll just move all of those objects to that layer. And then we will have... what do we call this layer? Lines. I'll just call it lines, and I'll make it red. There we go. And in this layer, we will draw these line segments here. Okay, so we have one going down here, and these can't be polylines, these need to be separate line segments. So stuff like that, and then we have this, and we have that. Okay, so we have this very, very simple pattern. And I guess now it's time to actually make it into, you know, kind of convert it into a mesh and start messing around with it in Grasshopper. Okay, so first things first, let me reference in these rectangles into a curve component. So I'll select these 8 rectangles. I'm not selecting the lines, by the way. And I'll right click on the curve component and set multiple curves. There we go. So now these are set, and actually maybe I should hide them. Or no, it doesn't matter. And then we have these line segments here. So I'll make another curve component. And I will select these line segments. Right click, set multiple curves. Now we have these line segments here as well. Actually, I'll group these components separately, and I'll call this base grid, and I'll call this smocking lines. Yeah, that should do the trick. Okay, so now we need to be able to kind of array this to any size that we want, right? So we want to be able to just kind of keep arraying this over and over. So how do we do that? Well, first things first, base grid here, I want to make this into a mesh, right? Because I don't want to deal with curves anymore here in Grasshopper. So I'll make this into a mesh, and the easiest way to do it is by using a tool node that's called Simple Mesh, which will recognize every rectangle as a mesh face, right? So as a single mesh polygon. So what we get here is 8 separate meshes, which have, 4 vertices and 1 face. That's super. And I will use those those 8 meshes to, let's use combine and clean. That's not how you write combine. Combine and clean. That comes with Kangaroo 2. And now we have one single cleaned up mesh. Okay, that's good. And now for the curves, I want them to be kind of arraying as a group. So I'll just use a group component here. So we package these 4 curves into a single object, which is a group in Grasshopper. And I will, let me move it here. I will merge these 2 guys together into one list, right? So if I look at what this list has, it has a mesh, right? And it has a group with 4 objects. Easy. And those 4 objects are, of course, these curves here, these lines. Okay, so now it's time to array. Array. Let's use just a regular rectangular array, I guess. Rectangular array. And the geometry that we're arraying is going to be... No, sorry. Before we array, I want to group this again into... let's package this even further. So I'll group... Oh, that's not that. Group. I'll group these 2, the mesh and group of 4 objects into one single group. So you can think of it as me just packaging everything into these boxes, right? So just a big cluster of things here. Okay, let me keep hiding things so that nothing is in the way. And now let's array. Okay, we have it arrayed. But the size, of course, is very bad. So the step size of the array is calculated through a rectangular cell size, right? So we need a rectangle that contains that is like a boundary rectangle for all of our geometry that we have so far. And to do that, let's just use bounding box. Bounding box, there we go. And what it gives us as an output, it gives us a flat box, meaning it's basically a rectangle, right? So we can just use that as a cell, and now it's going to array properly. All right, so now we have full control over how many times do we repeat this. And I think I'm going to repeat it like, let's say 5 times in X and 7 times in Y. Maybe let's go for 5 and 5, and then we'll switch it up if we don't like it. But basically here we can just control, you know, how many do we have. Okay, so for now everything is flat, right? And we, as I mentioned before in the video, we want it to be a column, right? So it doesn't really work since it's flat. But what we can do is we can make a cylinder here. And let me just make it here. So a cylinder and something like that, right? I'm not that, you know, I don't care about the size of the cylinder. Actually, maybe I want it to be a little bit taller though. Okay. And I will explode the cylinder and just get rid of the top and the bottom here. So it's basically just a tube. The nice thing about this is it's a single surface, right? Meaning we can map this flat pattern onto the surface. So by using this technique, you can map the flat pattern on any kind of a untrimmed single surface. But in this case, I'm just using a cylinder. We don't need to go all fancy with this. And in Rhino, the thing that the tool that does that is called flow along surface, but in Grasshopper it's actually something else. So it's under translation or under transform, morph, and I believe it's sporp. I don't know what's up with the name of it, but yeah, sporp. Sure. So it has a lot of inputs, but those are very easy to work with. So first input is base geometry, right? So it's what are you going to map? So it's going to be all of our stuff here, right? So I'm just going to take all of our groups here, 25 groups in total, and I'll say that those groups, those arrayed groups, are going to be transferred from flat piece to a cylindrical piece, or a flat surface to a cylindrical surface. Then it asks me for base surface. Well, we don't have one yet, but as you can probably tell from this tool right here, we can just kind of keep on using the bounding box tool. As long as it's flat, it's going to just give us a surface. So I'll say bounding box. Oh, and keep in mind that when you just use a bounding box on this arrayed geometry, since it's per object, it's going to give you 25 bounding boxes, right? So I need to right click on the bounding box tool and choose union box, and then it's going to give me only one bounding box for all of them. And it's a flat box, so I don't think it's gonna work just like that. I'm not sure, but just to be sure that it works, we can use deconstruct brep, and it gives us one face, which is an untrimmed surface, and we just connect it to S0 input here as our base surface. Okay, so we're morphing this pattern from this surface, and then it asks us for UV parameter for orientation, right? So actually we don't really care about this. We'll just use the first point on the surface, UV at 0, 0, as well as we'll use UV at 0, 0 for this cylindrical surface right here. So I'll just create a panel, / enter, double click on it, and I'll just type in 0, 0. 0, 0 means it's going to probably be bottom left corner of this surface. I'll just connect it to, oh, by the way, with the panel, don't hit enter because that's just going to create another line of text. Just click outside once you're done. You don't want to have more than one line of text. Okay, so we have the first part of this setup, and then the second part is target surface. So that's going to be our cylinder. Let me reference it in as an SRF surface. Set one surface. There we go, and let me hide the cylinder. There we go. And then UV parameter on target surface. I'll just reuse the same panel. Why not? And rigid geometry will not be deformed as it's transformed. Yes, that's... I need to think about this. For now, let's keep it as false, but if this doesn't work, we will know what's the culprit. Okay, so what do we have here? Well, we have a bunch of groups, right? So everything seems to be working correctly. Nice. And let me hide that so that it's not in the way, and now we'll just continue working with this guy. So here we have 25 groups that are wrapping around this cylinder, and I will use ungroup on them. So I have ungrouped them, and now we have 25 branches. And let me actually right click. You need to do this as well. Right click on the output and choose simplify to kind of simplify the tree. So we have 25 branches from those 25 groups, and in each branch we have 2 elements. And those elements are the meshes and the lines, right? So let me separate them by using explode tree, like that. And why are you doing this? Oh, whoops. We need to do one more thing. So if I look at it with a panel, I can see I have 25 branches with always first element being the mesh and second element being the lines, the group of lines that are going to contract. That's good and all, but I want to separate all meshes and all groups into separate like outputs, right? So to do that, I can say flip matrix, and what this will do is it's going to take all of the meshes that are 0, that are in index 0 in each branch, and they're going to put them all or group them all into a new branch. And then they're going to take all of the groups that are in index 1 in each branch, and they're going to group them into their own branch. So visually, I guess visually it's easier to show you. Visually we have a tree. Let's do this and this. So visually we had a data tree with 25 branches and 2 elements in each branch. After flip matrix, we have 2 branches with 25 elements in each branch. So it kind of flipped the logic. And now I can use explode, I can use bang right here. And now we have separated all of the meshes into one output and all of the groups of lines into another output. All right. So now let's deal with the meshes first, right? So I want to join them up, right? And I'll use combine and clean for this. So all of the meshes are joined up now, and I will use basically we need more resolution, and I can't use Catmull-Clark subdivision for this. I need to use something else, and the reason why I can't use Catmull-Clark subdivision, basically let me just preview, custom preview, swatch, let's make it black like so. Okay, so if I were to use Catmull-Clark subdivision, and let's use level of 2, whatever, that doesn't matter. See how these lines disconnect from the mesh? That's because Catmull-Clark smooths it out. Even if I use fixed, is it style? No, setting. If I use fixed or smoothing, it doesn't matter. Only the top parts get fixed, but the inner parts, they still get smoothed out, meaning that the mesh moves away from these lines that we have here. We can't have that. So Catmull-Clark is out of the question. Instead of Catmull-Clark, I will use constant quads subdivision. So here we have our clean mesh, and I'll just connect it to our split quads tool, and I will use level of 2 for it. And now you can see that all of these lines they stay on the polygons, which is super for us. Okay, we have that going. That's very nice. That's very good. Can I actually, just to be sure, I'll choose fixed, just to be sure. So here I right click on it, on the S input, and I choose fixed so that nothing moves. Everything is as it is. We just have more polygons. And this is important to do because the more polygons you have, the more precise the calculation is going to be, the simulation is going to be. Okay, now it's time to actually start creating a simulation script. Right, so how do we simulate this? We'll use Kangaroo for this, of course, and I'll go for always when working with Kangaroo, I go backwards, right? Usually you go from left to right, and in this case, I go backwards because Kangaroo is always, like, you set it up always in the same way. So I will create a solver, which will always have a toggle, you know, to turn it on or off, and it's always going to have a button to reset it, right? And then for goal objects, I will say entwine. I will create a data tree where there's going to be only 2 inputs, 0, 0 and 0, 1. And you can add or remove inputs by clicking on these. You zoom in and then you can click on these plus minus signs. Okay, so a data tree with 2 inputs is going to come in. Why is it like that? That's because I will use goal show as my 0, 0 input, and all other like physics-based goals are going to be placed in here, plugged in here. And I will have definitely more than 1, so I'll use merge for all of them. There we go. So I'll merge a bunch of inputs here, and also merge works in the same way. You can keep adding inputs when you zoom in. Okay, so since 2 data branches are going to come into the solver, 2 data branches are going to come out, right? So I'll use explode tree here, just like that. And I know that show, which actually, you know, a goal that says give me the geometry, comes in at 0, 0, meaning that after I explode the tree, why are you freaking out? Oh, that's because of this. Doesn't matter. So since show comes in first, right? It's going to the mesh is going to come out first. So the important part is going to be here. And let me just create a mesh container, just like that. And what do we do with it? Yeah, for now, let's just maybe let's make it pretty. So preview, custom preview, just like that. There we go. Okay. So this is my setup, and I should probably, yeah, whatever. I should just have it as a separate file and just keep kind of copying it in, because this is always the same for any simulation that I do. So let's start dealing with goals, and there we are going to have a lot of them. So the first goal is show, which is whatever. It's just our mesh, and let me actually do this and just connect it to show, just like that. And now we have way too many things, so I will hide literally everything except for the two previews. And now basically our simulation goes like this. You tell the solver to show you the mesh, it shows you the mesh, and that's it, right? So it's not a fun simulation for now. All right, so now let's make it fun. Where do we start? So think of it this way. This mesh right here, this pink mesh, is basically like a tube of fabric, and you pour concrete into that tube, right? And then you will contract these edges, these lines, to create a pattern. All right, so first things first, fabric cannot be infinitely stretchy, right? It needs to it needs to be able to withstand certain amount of pressure and torsion. So the first thing for this mesh that we have here, the first goal is going to be edge lengths, right? The mesh, all of these edges, they are going to try and keep their original length, meaning that the fabric will not be able to stretch freely or infinitely. So edge length asks us for three inputs: mesh, length factor, and strength. Okay, so for the mesh, we could use this, but what I prefer to do is I prefer to triangulate the mesh first to get more edges. And this is not a clean way of how to do it. There's actually a cleaner way, but don't worry about it. So this is a triangulated mesh right here, right? You can see that it converts every quad into two triangles. And then with edge lengths, we just feed it into edge length. So all of these lines will try to keep their original length. Okay. Length factor, by default, it's set to 1, meaning it tries to keep the original length, and that's perfect. Strength, it's set to 1. Maybe 1 is fine. We will see. It's hard to tell right now. So let's say edge length strength is 1. Okay. So I connected there. And now if I run this reset, and if I run the simulation, nothing happens. That's because, it's basically we have two goals. One is show, and let me move it here. One is show, and the other one is just stay as you are, right? So it just does that, and nothing happens. Okay, so now, and let me say stiff fabric, there we go, show mesh. So I'll keep naming the goals so that we don't get lost, because we will have quite a few. okay, so we have a piece of fabric here, and we're pouring in concrete, right, into this piece of fabric. How is it going to behave? Well, or rather, what kind of physical things are going to happen with it? Well, it's going to inflate, right? And it's going to inflate because there's going to be pressure involved in how it inflates. So pressure-wise, it always will, all of these polygons are going to try and move outwards, right? So, okay, do we have a goal for that? Load, we could use load, but there should be, for a mesh, yeah, there we go, pressure, super. So we will use pressure, which asks us to give it a mesh, and we will use this triangular mesh here, just like that. And for pressure strength, I think when it's set to 1, it's just going to explode. Let's see. Reset, run, yep. just explodes. So it applies pressure to every polygon, and we have quite a few. So we can't have a pressure that is so high. Instead, I will say 0.04. I don't know, I just 0.05, 0.04. I just want a slider that's between 0 and 1. And 0.01, sorry, between 0 and 0.1, there we go. So 0.04 or 0.05, whatever. Reset, run, still inflating like crazy. Less, 0.02. Still inflating like crazy. Oh, wait. Now it's coming back. Still inflating. Okay. Even less. Okay, 0.005. Reset. Okay. So this kind of works a little bit. Okay. So for this particular mesh, and by the way, the more polygons you have, the less strength you will need to use. So apply pressure from concrete. Okay, that's good. So we have that done. We have 2 goals here, 3 goals actually that are done. So now we need to start using those lines to actually kind of create a pattern, right? So what do we have here? If I look at the output, it's a bunch of groups, right? So I need to ungroup this output, and we have a data tree, and we absolutely don't care about the data tree. So I'll flatten it out, and we have a bunch of lines. And my next goal, and let me just do that. So my next goal is going to be, all of these lines need to contract. Okay. So there is a goal that's called length line right here. Length line. It's not just a curved length. It's basically, it actually makes the line change its length. Okay, sure, let's use that. So for this goal, it asks us for 3 inputs as well. First one is line. Okay, sure. We just do that straight up. Let me hide that. Okay, and then we have length. Right, so what's the length of the lines that we, how long should the lines try and become? 0, right? Straight up 0. Okay, Jesus, come on, just let me move the panel here. There we go, 0. And then strength, ooh, that's a tough one. Let's create a slider between 0 dot 10, 10.0. So a slider that goes from 0 until 10, and for now let's have it at 0 and just connect it like that. Okay, reset. Let's run this. Okay, so it's doing its thing, it's inflating. And now let's increase the strength. Okay. It does its thing, and then it all falls apart, right? If I increase the strength even more, you know, completely destroyed. All right. So it does work, but we still need more goals for this to work cleanly. So let me call this contract lines, or contract smocking lines. There we go. Okay, what's next? So as it's contracting, stuff starts kind of folding into itself and starts kind of like these loops of fabric start forming, and everything kind of collapses onto itself. So we need collisions. Unfortunately, we do need collisions for this, and I say unfortunately because it's a very slow, like calculation wise it becomes quite slow. So for this I will use sphere collide, which asks me to give it points, and I will give it points from this mesh right here, or from the triangulated mesh, doesn't really matter. I'll use this original mesh right here, and I'll say WBV, Weaverbird's vertices component, or you can just go to Weaverbird, extract Weaverbird's vertices component right here. Okay, so I'll connect mesh to this vertices component. It gives me all of the points, and I'll say that those points need to go in here. Okay. So think of it this way, the way collisions work is it creates a sphere, mesh sphere. It creates a sphere around every point, and definitely not that big. I believe the radius by default is set to 1. Yes, it is. So it creates a sphere around each point, and those spheres will bounce off from each other, right, as the simulation runs. So for now, 1 actually seems to be quite a pretty damn decent. That seems to be a pretty decent size, but we want it to be automated. If we change the mesh, we want it to automatically kind of change its dimensions. So how do we do that? Well, from this mesh, I will get its edges as well. So Weaverbird's mesh edges. Extract Weaverbird's mesh edges. So I extract the edges from this mesh. And let me move them somewhere here. And I will say, okay, what's the length of these edges, right? So it gives me a bunch of numbers. And I'll say, no, just give me an average. Average... average, there we go, average length. Okay, so it gives me an average length of 2.9, and if I plug it into the radius, it actually, like 2.9 means, you know, it's whatever, it's an average length. So let's say we get the edge length of this. So we need the radius of the sphere to be definitely less than half, so that those don't kind of start hitting each other immediately. So I will take this number and I will divide it by 3, just like that. So now the sphere will reach only 1/3 of the line, but that should be definitely good enough. And for strength, this needs to be a pretty intense. Like collisions are always like pretty strong in the simulation. So I'll use strength of 100, like that. Let me group it, and let me call this collisions. I don't know if that's how you write collisions, but that's how I write collisions. Okay, so we have collisions here. Let's check it out. Run. It inflates. And now let's increase the strength. It contracts, but now it's a bit better, right? It still is a, you know, kind of wishy-washy, but it's definitely better. And actually, let me make it even better. It's still low resolution here, and I'm doing it, you know, I do want it to stay low resolution. Actually, can we? What if I increase the level of subdivisions here? No, for now, let's keep it low res. But here, I can actually increase the resolution by just using Catmull-Clark subdivision on it. Just like that. You know, Catmull-Clark subdivision will subdivide the form even further, and we end up with something like this. Whew, getting there. Definitely, you know, far from being a column, but because it contracts way too much, but you know, we're getting there. We're getting there. So let me reset, and let's see what else we can do. Well, first of all, I want to use smooth. So smooth go, the iron icon. And I want to smooth out this initial mesh before triangulation, this original mesh. And I will use a smoothing strength of, what's the strength here? 1, sure. So this just helps it be a bit more smoother. Shouldn't change it too much, but actually let's see. Yeah, you can see now it's a bit smoother as it's kind of contracting. Okay. Smooth it up. Okay. That's so many goals. Okay, last part, I promise, or rather last goal, is going to be not letting it leave the bottom, and also the top. Let's say we anchor the whole top and we just let it kind of let's say we have the top of this fabric, right? We would have a certain bracing system for the top. Yeah, we would have a bracing system for the top so that it stays flat. And then we would say, okay, and now just slowly move down, but not too much, while the bottom would probably be completely locked in place, right? Yeah, so let's do this. We have our mesh here, so I will extract all of the naked vertices of this mesh, NV, naked vertices. Okay, well, that's not all naked. It shows all of the vertices, but I will only take out naked points, which are in the bottom and in the top, right? Those are points around openings. And I will say, well, I need to separate them. I need to separate them into the top portion and the bottom portion, because I will treat them a little bit differently. So let's see these points. How are they different, the top group and the bottom group? Well, the top group is higher, right? So I can deconstruct, that's not that, deconstruct those points into their XYZ coordinates, right? And I can say, okay, what's the average? What's the average Z coordinate, right? 67. So it's, you know, somewhere in the middle, in between these two groups. And I'll ask, okay, are these numbers higher or lower than the average? So let's say larger. Are these numbers larger than the average? And then we have a bunch of true and false statements, you know, answers. It's above or it's below, right? These are the answers. And I can use those answers as dispatch, as a pattern for dispatching this list into two separate lists, A and B. One is, like A output is going to be all of the points that are above, I believe. Let's see. Point. Yeah, A output are all of the points that are above, and B output are all of the points that are below. Super. Okay, so we have that going on, and let me make it more compact. There we go. Okay, and now we need to think about how do we treat the ones that are, let's say how do we treat the ones that are below? That's going to be a bit easier. Or well, these are in the top, so let's start with the top. Okay, first of all, I want these guys to stay coplanar, meaning they need to stay in the same plane. Coplanar. It's, I believe in Kangaroo, it's under goals coplanar. There we go. So these points with a strength of, I don't know, what's the default? That's 1. No, we need it to be pretty strong to make them stay. So I'll say 100 or 10. Let's go for 100. Sure. I do want them to be. But then this might mess up. Let's go for 10. So instead of 1, I'll use a strength of 10 for this. And that's going to be one more goal. So now, actually, let's move up. Let's move this back here. And let's call this top stays flat. Sure. That's our goal for the top, and let's see if it actually works. Reset, run. They don't give a shit, do they? Wait, what if we strength 100? Strength 1,000. What the? Why do you not care? Ah, wait. No, with 1,000 they stay flat. Yeah, that's good. Front view. There we go. So these guys are flat. Nice. Okay, so we have that going on. And will it work with 100? Will it work with 10? With 10 it kind of starts going all over the place, right? Let me reset and just see. Yeah, with 10 it messes up. So actually for now let's use 1,000. Why not? If it works, it works. And then I wanted, I want these guys in the top to be anchored, but not too much. How do we do that? I believe there's an anchor, plastic anchor. I don't know how it works though. Well, let's figure it out. Plastic anchor. For these points as well, limit distance at which target point starts to slide. Okay. Strength 1. Okay. Sure. Reset false. Let's just see if it helps at all. So those are our plastic anchors now. Reset. Oh boy, yeah. Nice. So it slid a little bit and then stopped. Okay, so we have that going on. Getting there. Okay. And now for the bottom part. So bottom part will be nailed down, right? But I don't want to just nail it down, you know, just use these bottom points as, as anchors. I want to actually let them change, let them move around freely on an X and Y plane, but they can't move up or down. I know it's not that realistic, but whatever. We don't care. So what? Goals point, anchor XYZ. Is this the guy that we want? Point, yes, super. Okay, so we anchor down these bottom points, but we don't, so it's false for X, false for Y, but true for Z. So we only anchor it, anchor them, toggle, in Z direction. So they can't move up or down, but they can move left to right and back and front, back and forward. And the strength is 1000, that's fine. I'll just connect that to the 8 input. And I believe that's, yeah, that's enough of goals for today. Plastic anchor, it's basically, let's just call it, don't move too much. Top, don't move too much. And anchor XYZ, bottom, only move in XY, not in Z. Okay. So we have that, we have that. Whew, that's a lot of goals right there. But what can you do? Moment of truth, I guess. Let's go for perspective view. Let's make this nice. Gray is definitely not the nice one. Something like that. Let's do level 2 for Catmull-Clark subdivision, not level 1, so that it's even nicer. Reset, run. All right, there it is. There it is. We have a working script. And can I increase, let's say I increase the strength. So it does that. Let's say I increase the pressure. So it does that. And now Actually, the anchoring in the top stopped it. That's nice. Okay, we have it going. We have it going. Nice. Then you can just bake it out. Show a default layer. And you have yourself, can I use fill mesh holes? Yes, I can. 3D printable. Let's check. What? Closed polygon mesh. Super. You can print this out and have it as a, I don't know, a column or a table leg, whatever thing. Emap. Arches. Where's my display? Mesh wires, turn that one off. I have absolutely no complaints about this mesh right here. No need to improve it any further. So things that you are able to change, of course, the pattern. You know, you can mess around with the pattern as you please, and it's going to, so now I've just moved the line, and also of course you can increase and decrease. You can add any pattern you want. So I just moved the line, and let's reset, and now, you know, this is with a different smoking pattern. This one is also kind of cool. Anyway, that's that. Let me move it back. What else can you do? You can, of course, show selected. You can change the cylinder, right? You cannot just change it, but you can kind of do this kind of stuff with it. And then reset, run, you know, still works. Everything's fine, neat and dandy. I believe it's still going to, it's still going to kind of converge to a cylinder. It's still going to try and find, you know, that kind of resting position. So it's going to try and stay as a cylinder. Then what else can you do? Reset. You can change the resolution, right? 7. Just give it some time. 7 means more of these lines here. You can change the initial resolution of the split quads, meaning that you can run the simulation with more polygons if you have a better computer than I do, and it's going to run nicer. So for now, let me reset and run this. Looks nice. Okay, and I believe we are done, right? Nothing else to do here. False. So, hope everyone enjoyed this one. I sure have. It's always nice to work with these patterns and kind of investigate what kind of effect you can get. And again, like using this fabric, this kind of stitching fabric, like you have a flat piece of fabric and you just stitch it together and kind of use these smocking methods to create shell, not a shell, crap, what's the name of it? Formwork. A formwork for concrete. I think this is brilliant. It introduces so much nice complexity with not a lot of costs, right? And again, Annie and her research is definitely something that you should check out. It's really, really interesting. I'll leave probably a link in the video description, as well as a link to my Patreon page, or this channel's Patreon page, where you can support the channel, and then you will get this definition and all future and other definitions that we do here on the channel for free. But of course, you know, if you don't want to do that, just follow along, you know, with this tutorial, and you'll have the definition either way. So it's up to you. Again, hope you enjoyed it, and I will see you in a few days.